Okay, so in today's chapter summary, we are going to be looking at Chapter 9, Vectors from Core Pure Year 1 for further maths. Now, as I always say in these videos, it is not possible for these chapter summaries to cover all of the possible ways that you can be assessed on this topic. So please make sure this is just being used as some quick revision rather than to teach you the topic. And of course, you're going to need to look at proper exam questions for this as well. Now, this is a huge topic. I think this is going to be about 1 hour, this video. But I'm going to remind us it's really just about a lot of skills. This is quite different to some of the other chapters that are focused on problem solving. There is a lot of skills within this vectors chapter. So let's dive straight in, and we'll be looking at how do we form the equation of lines and planes in lots of different kinds of forms here. So for this first question, we're going to try and find the equation of a line that goes through two coordinates, and we're going to do it in vector form and in Cartesian form. So to remind us, R is a general point on the line, A is a specific point or coordinate that's on the line, and B is the direction of the line or the a vector that is parallel to that line. And it's R equals A plus lambda B, where lambda is the parameter that varies to get you to various different points on the line. In the Cartesian form, the denominators B1, B2, B3 are the components of the B vector, and in the numerator, the thing that's being subtracted from the X, the Y, and the Z are the components of the A vector, A1, A2, and A3. So you know what to do for this. All you really need to do is to find out the direction vector. So the direction vector for this case, we'll do one of them, subtract the other. For some reason, I always do the second minus the first, but it won't really matter. So if I do the second one and I subtract the first one, we end up with 2 minus minus 1 is 3, 6 minus 2 is 4, and 0 minus 4 is minus 4 for this one. Of course, if I subtracted it the other way around, it would be minus 3, minus 4, and positive 4. And because it's direction vectors, you can scale this up or down however you want to, because it's not referring to a coordinate. We're just talking about things being parallel. So the vector form is going to be R equals A plus lambda B. Pick either of the coordinates. I'm just going to go for the first one, and I'm going to do lambda lots of the direction vector, which is 3, 4, and minus 4. So the Cartesian version, well, it's going to be this kind of setup, isn't it? An x minus something, a y minus something, and a z minus something with our denominators. The denominators are just going to be these components of the direction vector, so the 3, the 4, and the minus 4. And you can pick either of these coordinates. I'm going to use this one, so it would be x minus minus 1, in other words, a plus 1, y minus 2, and z minus 4 for this. The next question asks us to find the equation of the plane containing these three coordinates. Notice how two of the coordinates are exactly the same as these ones that we've got here. We've just got this third coordinate. Now, when we have these three coordinates, we have 1, 2, 3 of them. One of them can be referring to, like, on the plane. We're then going to need to find two vectors that are parallel to the plane like this. And we're going to do three forms: the parametric form, the scalar product form, and the Cartesian form for this. So when we do this, we are going to need to use this fact. I've skipped over a lot of things to do with magnitudes of vectors and the definition of the dot product. You're doing further maths and you should know this without too much reminder. But I have got this reminder that if A dot B equals 0, then A and B are perpendicular to each other. Also, R is still a general point on the plane. A is a specific point or coordinate on the plane. And B and C are direction vectors that are on the plane or parallel to the plane. And when we get to this version, the scalar dot product form, we use n, which is a normal to the plane, meaning perpendicular to the plane. And then we have this Cartesian version down here, where n1, n2, and n3 are referring to the components of the normal vector that we've got there. So in this diagram, these are all referring to different points, which any of these three could be A. But then when you subtract them to find a vector between 2 points, those are going to be the B and the C that we've got at this point here. I'm probably just going to take this one as my A that we've got here. So this is when I'm talking about the scalar, not the scalar, but the parametric form like this. So I'm just going to take my A is minus 1, 2, and 4. Now B, in this case, is going to be where you've subtracted two of the vectors. And if I do this one, subtract this one, I've actually already done that over here. So I'm going to save a bit of time, and I'm going to say that this direction vector is going to be 3, 4, minus 4. And if I just want to find a third one, I'm going to do this one, subtract this, or this one, subtract this. It really doesn't matter as long as you're subtracting a different pair. So I'm going to do the 5, 8, minus 3, and from that I'll subtract the minus 1, the 2, and the 4 for this. 5 minus minus 1 is 6, 8 minus 2 is 6, and minus 3 minus 4 is minus 7. So for my parametric, this is probably the easiest one to form, because all you need is three coordinates. The parametric version of this is just going to be that R is equal to A plus lambda lots of a vector that is parallel to the plane, in this case 3, 4, minus 4, plus mu lots of 6, 6, minus 7, which is the other one that we've got there. Now for the scalar form that we're going to do, the scalar dot form, or the scalar product form that they call it sometimes, we need to find a vector n which is going to be perpendicular to the plane. That means that it needs to be perpendicular to this vector and to this vector. It needs to be perpendicular to both of these things. So the aim of this is we are going to find a vector n, which I'm just going to call x, y, z. We're going to find out what x, y, and z are, such that when you do n dotted with b, you get 0. In other words, they're perpendicular. And n dotted with c is also equal to 0, so that they are perpendicular. So this means that x, y, z dotted with the b vector, which is 3, 4, minus 4, has to be equal to 0. And my n vector x, y, z dotted with the c vector, which we've gone with 6, 6, and minus 7, has also got to be equal to 0. When you do the dot product, you get your 3x plus 4y minus 4z is equal to 0 for this. And then you get your 6x plus 6y minus 7z is equal to 0. And all we're really trying to do is find a value of x, y, and z that make both of these equations true. Okay, that's the only thing we're really trying to do here. Now, I don't advise when you pick a value for one of these things to pick 0, because you then might come up with a very trivial solution of x is 0, y is 0, and z is 0. Yeah, that's true. If x is 0, y is 0, and z is 0, you do get both of these equations completely correct, but then you just have that your normal vector is 0, 0, 0, which isn't going to help us actually form this equation that we've got here. So what we're going to do instead is we're going to pick a value for z to be equal to. Okay, I've maybe done that arrow a little bit big. Let's just go over here. So, boxing this off, we're now going to say, let's just pick a value. Let's just let z equal 1. Well, for that first equation, if z was equal to 1, we would have 3x plus 4y minus 4 equals 0. So I'll just put that minus 4 to the other side. And for the second equation, we would have our 6x plus 6y minus 7 equals 0. Put the minus 7 to the other side, and we get a 7. So I'm just trying to find some coordinates that will make both of these things true. Simultaneous equations, 3, 4, 4, 6, 6, 7. This tells me that when z is equal to 1, x is equal to 2/3, y is equal to 1/2, and that was when z is equal to 1. So this is telling me that my normal vector is 2/3, 1/2, 1, or, because I can scale this up here, I can multiply all of these things by 6. The reason I'm going to multiply them by 6 is because then it will get rid of both of the third part and the half part, and I'll have some integers. But if you don't want to do that, it isn't totally necessary. It's just we tend to do this with integers. So 2/3 times 6 is 4, half of 6 is 3, and 1 times 6 is this that we've got here. So just to finish off, as I jump up to this last part of the screen here, I'm going to do my r dot n is equal to a dot n. Now, a is just one of the coordinates. You can pick any one of these coordinates, and I guarantee you will always get the same value on the right-hand side. But my value, I'm going to do the -1, the 2, and the 4. So I'm going to do the -1, the 2, and the 4, and I will be dotting that with the 4, the 3, and the 6. So our scalar product equation, the r dot 436. Now, you know to do this. We don't need to do the full working. It's going to be -4 plus 6 plus 24, and that is equal to 26. And then the last stage to get our Cartesian equation for this is you're almost just imagining that instead of there being r, you just have it as x, y, z. So you would get the 4 times the x, the 3 times the y, and the 6 times the z, and that is equal to 26 for that Cartesian one that we have down here. So that's how we can form these different equations that we've got. Generally, you're going to find that the scalar product form and the Cartesian form are the most useful. The parametric is the easiest one to kind of build up from 3 coordinates, but it's not very useful for some of the things that we're going to want to do later on in this question. So let me just write this as the scalar product form so it looks nice and neat for our notes. Well, I say neat, not exactly neat, is it? Now, what do we do with these things? Once we've got the equations of planes and lines and stuff, we are quite interested in how things intersect with each other. And we're going to begin by having a look at 2 lines. We start looking at lines and planes, and then we look at another one with lines and planes, and then some stuff with 2 planes as well. So, we're going to look at whether these 2 lines here and here, whether they are parallel, skew, or whether they intersect each other. If they are parallel, then they have the same directions. If they are skew, they are not parallel, but they also don't intersect. Obviously, parallel lines don't intersect, do they? If they do intersect, you equate those lines and you check if all of the components can be the same. If they can't all be the same, then they're not going to be in the exact same place, so they can't be intersecting. Okay. I think what I'm going to do is get this out of the Cartesian form. I prefer it in that vector form. I think that's a little bit easier for us to deal with. So if I was going to write this in the vector form, the a coordinate is from the numerator is going to be the 2, the -1, and the 1. And the direction vector is 3, 4, 1. I've already got lambda in this question, so I'm going to use it with mu. I think I can immediately see that these are not parallel. This one and this one are not parallel to each other because they are not multiples of each other. So I'm just going to write that down, that 3, 4, 1 and 2, 3, -1 are not multiples of each other. So they're not parallel. Now, the next thing to investigate is, do they intersect each other? And you'll see I often like to write things when they are sort of two separate vectors as just one single vector. And I'll start off with this one that's over here. So that would be a 2 plus 3 mu, a -1 plus 4 mu, and a 1 plus mu. And you equate them. So I'm going to equate it to this side. That's a 0 plus 2 lambda, a 2 plus 3 lambda, and a 4 minus lambda. We said in the instructions we're going to check if all of the components can be the same. So from the I components, we have a 2 plus 3 mu is equal to a 2 lambda. For the J component, we have the -1 plus 4 mu equals 2 plus 3 lambda. And I'll check the K in just a second, but I've got enough information here to do some simultaneous equations. So I'll put them in a standard form. I'll put the -3 mu over to the right side like that. -1 minus 2 is -3, and I'll have the 3 lambda minus 4 mu. These are further maths videos, so you'll see I probably do some of these things a bit quicker. You can always pause the video and check that you're doing all of this correctly as well. So I'm just going to put all of this in my simultaneous equation solver on my calculator. I'm actually just putting this one and this one in the equation solver. And what I then end up with is that lambda is equal to -17 and mu is equal to -12. Okay. Now what I need to do is just to check this in the k coordinate, or in the k component. So I have 1 plus mu. I'm looking at this part and then this part. 1 plus mu, when mu is -12, is 1 minus 12, which is -11. And 4 minus lambda is going to be 4 minus -17, which is 4 plus 17, which is 21. And because -11 is not equal to 21, they don't intersect. So they don't intersect. So they don't intersect. Now, because they don't intersect and they're not parallel, hence the lines are skew. Whenever I'm thinking about skew lines, I always say they're kind of like, you know, in like heist movies where they're trying to get like the diamonds out of the museum or something, and there's these lasers. If you think of just like two lasers shining from like two different corners of the room that don't cross into each other, those are skew lines. They're not parallel and they are not intersecting with each other. Don't know why, that's kind of the example I always go to for this. Now what we're going to do is have a look at another example where this time we're talking about a line and a plane. And it says determine whether the following line and plane intersect, do not intersect, or if the line is contained in the plane. To do an intersection, literally just substitute the line into the plane and then solve it, okay? So, again, I'm going to rewrite this in a form that I like, and it's actually the same one as up here, okay? So that is just my 2 lambda, my 2 plus 3 lambda, and my 4 minus lambda. And then I'm going to substitute that into this equation. So this is 2 lots of the x part, the first bit, minus the y part, plus 3 lots of the z part, and that is equal to 14. 4 lambda minus 2 minus 3 lambda, plus 12 minus 3 lambda is equal to 14. Now for the lambdas, I have 4 minus 6 in total, so that's minus 2 lambda. I'll do the 14, take away 12, which is 2, add 2, which is 4, which means that lambda is equal to minus 2. So the fact we've just got one solution here, this is telling me that the planes do intersect. So that the line intersects the plane. This tells me that it intersects it intersects when lambda is equal to -2. Now, they haven't asked for the coordinate, but I can give the coordinate, okay? If I just say that lambda is -2 and I substitute it in here, I can say that that will happen at 2 times -2, 2 plus 3 times -2, and 4 minus -2. In other words, -4, 2 minus 6, which is -4, and 4 plus 2, which is 6. Or as a coordinate, they are intersecting at -4, -4, 6. What this looks like geometrically when you have a plane, there is a line, it is hitting the plane, it goes through the plane and comes out the other side like that. I've got another example here where there is a line and a plane. It is the same line as in the previous question. So we still have the 2 lambda, the 2 plus 3 lambda, and the 4 minus lambda. Apologies for my very messy writing there. And we're going to find out what happens with this one. Are they going to be this, this, or this? So I'm going to take that and substitute it into the plane. So there's going to be 3 lots of the x component plus the y component plus 9 lots of the z component being equal to 10. That is 6 lambda plus 2 plus 3 lambda plus 36 minus 9 lambda equals 10. And then something strange happened here. We have the 6 lambda, the 3 lambda, and the minus 9 lambda. They are all just completely cancelling out. Now, the fact that they're cancelling out gives us something very strange, because on the left we just have 38, and on the right we have 10, which is, of course, complete nonsense. This is impossible. And what this is telling us is there are no lambdas that make this true. There are no values for lambda to make it true, i.e., it does not intersect. Like, logically, we're saying no value of lambda will make this intersect. So what does that actually mean as a geometric interpretation? Well, we have the plane, right? And we have a line that is hovering above it and parallel to the plane. So actually, it does not intersect. We can even go further than this and say that the line is parallel to the plane. And I can prove this to you, because we know then that this is the direction of the line. This is the normal of the plane. There's my normal. There's the direction of the line. What do you think we know about those two things? If the plane is parallel to the line, the normal to the plane must be perpendicular to the line. In other words, n dotted with b should be equal to 0. N comes from here, which is the 3, 1, 9. If we dot that with the direction vector, which is the 2, 3, and the -1, we get 6 plus 3 minus 9, which is 0. Hence, they are parallel. Now, the only other thing that we would need to do that I haven't covered here is this one, the line being contained in the plane. If the line was contained in the plane, let's do a different one that would be kind of like this. The line is actually straight on top of it. We would need a different kind of plane, where instead of there being a 10 over here, there would need to be a 38, because what you would then end up with is that 38 is equal to 38, meaning it doesn't matter what value of lambda you pick, that plane and that line are always going to be intersecting. In other words, the plane is on top of the line. You could say it's parallel to it, but it's also contained on it as well. Now I'm going to get rid of all that purple writing, just so we've answered this specific question, but we've now talked about all 3 of those scenarios there. And then we're going to have a look at this one where we have 2 planes, and we'll determine the line of intersection between these non-parallel planes. Obviously, if we had parallel planes that looked like this here, they don't intersect each other. But if they are non-parallel, there will always be an intersection, because these planes are infinitely large. They're not like these squares or rectangles that I draw. So when we have these 2 planes like this, I'm going to start off by thinking here might be one of the planes, and then here might be another plane like this. We are talking about the way that they intersect along a line like this. Now, there are plenty of ways of doing this. There is a way of doing it in Further Pure 1, which uses the cross product, but I don't do that. I actually just use a Core Pure 1 method. You don't need to learn anything from Further Pure 1 to do this. The way I like to do this is you simply find 2 common points. A point that needs to be on both planes, you just do that twice, and you just find the equation of the line through these 2 points. There are other methods, but I will not be showcasing them here. So the aim is to find a point that is on both planes. You can see visually it's on both planes. Another point that is visually on both planes. And then you just find the equation of the line through them, just like we did in the very first example. Now, we have these two things. I'm just trying to find a coordinate, or in other words, an x, a y, and a z that will make both of these things true. Do you remember earlier on we did something kind of similar to this when we were trying to find out here and here we wanted to make both of these equations true? I said let's pick that z was equal to 1. Don't pick something that's equal to 0 because you might end up with 0, 0, 0. Here, we're not so concerned about that. Okay, just pick something really simple for z or for y or for x, and you can actually pick 0 here. You're just trying to find 3 coordinates that make them both true. So if I let z equal 0 for both of them, I get 2x plus 2y minus 0 equals 4, and I get 4x minus y plus 2 times 0 equals minus 2, and then I can just solve these simultaneously. So it's my 2, 2, 4, my 4, my minus 1, and my minus 2. We say that x is 0 and y is 2, and we've already said that z is 0. So this means that 0, not y is, I said y is 2 and then I wrote it down as a 0 from the calculator. X is 0, y is 2, and z is 0. So this means that 0, 2, 0 is on both planes. And you can manually check this if you really wanted to. If you have 0 in here, 2 in here, 0 in here, it does equal 4. 0 in here, 2 in here, 0 in here, it does equal minus 2. So we found a coordinate that's on both planes. You could do z equals 1, you could do z equals 500. I'm going to keep it simple. I'm going to do let's make y equals 0. So I then have 2x minus z equals 4. 4x plus 2z equals minus 2. And we're going to find out what the x coordinates and the y coordinate is just using the calculator for this. So it's 2x minus z is 4, 4x, 2z minus 2. I get, I don't know why I said that x is 0, we said that y is going to be 0. On my calculator, x is 3/4, y is 0, and z is minus 5 over 2. So this means that 3/4, 0, and minus 5 over 2 is on both planes. So all we need to do now is just find an equation of a line through this coordinate and this coordinate, as simple as that, really. So all I'm going to do now is to find out my direction vector. You can use the letter D or B. Let's find our direction. I'm going to do one of them subtract the other. So I will do 3/4 subtract 0. That's 3/4. 0 subtract 2. Minus 5 over 2 subtract 0. And we get this. I'm going to scale this up. So I'm going to scale it up. I'll probably scale it up by timesing this by 4, and by 4. So that my new one is just going to be 3 minus 8 and minus 10. So the equation of the intersection line, the equation of the line is r equals, well, the direction we've just said is 3 minus 8 and minus 10. And we can just pick either of those two yellow coordinates there. I'm just going to pick the simple one, the 0, 2, 0 that we've got. So you could have either coordinate here, and you could also have included this in its original form. You could even have 30 minus 80 minus 100. Remember, directions you can scale, positions you should not do any scaling. So we're going to do now what there is between angles of these different things. You can have two lines, a line in a plane, or two planes. Now the questions are all saying, what's the acute angle between these two lines, between this line in a plane and these two planes? I'm just going to quickly talk through these three formulae. Now these three formulae are all quite similar, right? The first one between two lines has cos theta, between a line and a plane has sine theta, and between two planes has cos theta. So if they're the same, it's cos theta. If they are different, it is sine theta. And the structure is exactly the same. The numerator are the direction vectors, dot product, and take the magnitude of that. I'll explain why in just a second. And the denominator is the magnitude of each of those direction vectors multiplied together. The difference with the a line and a plane is you have a direction vector for the line and the normal vector for the plane, but exact same structure. And for the plane, you go back to cos theta, you just use the normal vectors for both of them. Now the reason I have the modulus sign in the numerator is the modulus will ensure that you get an acute angle. When you do it for the line and the plane, the modulus of the numerator, meaning don't get a negative, it will ensure that your angle is positive and acute. This one, it doesn't matter so much, because if you get an obtuse angle, you can just do 180 minus the answer. But for this one, it's nicer to make sure that you definitely get a positive angle. It's much easier to interpret what's going on, but I just do it all the time. And again, down here, you just get that the modulus ensures that the angle is acute. So I will do the first one a little bit slower, and then I will go a little bit faster for the second one and the third one. So we're looking for the angle between these two lines. You must use the directions vectors for this. So this is that cos theta is equal to, I'm going to do the modulus of the dot product of these directions. That's the -2, the 1 and the 5, dotted with the 1, the 4 and the -1. Take the modulus of that. And then down here, I'm not even going to show you, it's further maths, right? I can just quickly do this one squared, this one squared, this one squared, and add them up together. So that's a 4, a 1, and a 25. That is just root 30. And then for the next one, the 1, the 4, and the 1, that's going to be a 1, a 16, and a 1. That's just an 18. I'm just going to write it as root 18. I know that root 18 is 3 root 2, but I just find this quicker to type on my calculator. And some of this is all about being speedy, ready for the exams. So the numerator is going to be the cross product, sorry, the dot product of these things. There's going to be a -2, then a 4, and then a -5. That's multiplying these and adding them together. And that comes to -3. And I've got those modulus signs around it. I'm not even going to bother simplifying this because it's all going to go in the calculator. So this is telling me when I take the magnitude of that numerator that it's 3 over root 30 root 18. And my last stage is literally just to do the inverse cos of this. So it's 3 divided by root 30 and root 18. I'll do the inverse cos of this, and theta is 82.6 degrees to 3 significant figures, okay? We're now going to do the same thing, but it's a line in a plane. Line in a plane is with sine theta. I will be using this direction vector, which is the same as before, and this normal vector. So let's see if we can go a little bit faster. It is going to be the modulus of the -215, dotted with the normal, which is 1, 2, -3. The 215 we already worked out from before, didn't we? It was root 30. And the 1, the 2, and the 3, that's a 1, a 4, and a 9. That's a root 14. So let's do this a bit quicker. That's a -2 and a +2. That cancels. And a -15, but there are modulus signs. So that is just 15. So it's 15 over the root 30 and the root 14. Meaning that when I do the inverse sign for this next stage, 15 over root 30 and root 14, inverse sign the answer, and you get 47.0 degrees to 3 significant figures. And then our last one, which I'm going to do even quicker, is determining the acute angle between two planes that we've got. So again, it's the same formula. We'll be using these as my n1 and n2, and of course it's cosine for this. So it's going to be the modulus of the 1, 2, -3, dotted with the 0, 2, -9. The 1, 2, 3, we already did the modulus of that over here, and it was root 14. And then I can do this. This is 0, 4 when it squares, and 81. 4 and 81 is 85, so I'm just going to write it like this. So cos theta is the numerator 0, 4, and 27. 4 and 27 is 31. So that's 31 over root 14 and root 85, meaning that we have 31 divided by root 14 and 85. Inverse cos the answer, and we get 26.0 degrees to 3 significant figures. Okay, next up is shortest distances. This is a pretty big one and one of the more challenging parts of vectors, I would say. So we're going to try and find the shortest distance between this coordinate and this line that we've got here. We are doing it between a point and a line. And the general approach is this. We're going to find a vector between the point and the line. So let's just do a quick diagram. Here's the point, here's the line. We're going to find a general vector between them like this. We are then going to try and make, it doesn't matter about the direction, whether it's that way or that way, by the way, although I think it doesn't matter. We're then going to make this vector perpendicular to the direction vector. In other words, we're going to make this red vector be perpendicular to the direction of the line. Because if they are perpendicular, then this here is the closest that it can get, it's the shortest distance. We solve for lambda, we sub back into this vector that we found here in 1, and we find the magnitude of this line to find the distance, to find that actual shortest distance that we have. So this is ideally what we're looking for, the length of that red vector that we have got like this, okay? Again, if you've watched the videos, you should understand what all of this means. It's really just here as a bit of a refresher and a bit of a reminder for this. So to begin with, I'm going to rewrite this as 2 minus 4 and 2, just want it in vector form, and I'm going to write this one as lambda, 2 plus 2 lambda, and 6 minus lambda, okay? We are then looking for this vector between the point and the line. It was red on the diagram, so I'm going to do it here. Vector, do it red here, vector between point and line. Just do one, subtract the other, okay? So that's my lambda, 2 plus 2 lambda, 6 minus lambda, and I'm going to subtract the 2, the minus 4, and the 2. If you think you can just do that without writing this out again, and you can just do it from here, then you should do that and just check it really carefully. But I'm trying to be a little bit more detailed for the sake of this video. So for the numbers, we've got 2 minus minus 4, which is 6, and you still have the 2 lambda, and the 6 minus 2 is 4, and we still have the minus lambda that looks like this. So there is our red vector that we've got there. We are now going to make this red vector perpendicular to the direction vector, okay? So this means that I want the lambda minus 2, the 6 plus 2 lambda, and the 4 minus lambda, I want to dot it with the direction vector, which is 1, 2, and minus 1, 1, 2, and minus 1. I want to make them equal to 0. So I get the lambda and the minus 2. I'm going to double that next bit, which is a 12 plus 4 lambda, and then I'm going to do the minus 4 plus lambda for that last part, which gives me lambda plus 4 lambda plus lambda, that is 6 lambda for this. And then when I put the 4 and the 2 to the other side, I get 6. Subtract 12, 6 subtract 12 is minus 6, meaning that lambda is equal to minus 1. So we have now done this. We have done the vector between the point and line, which was red. We made it perpendicular to it. We've solved it for lambda, and we're going to now sub it back into the vector that was found over here. In other words, we're trying to find out what this vector is, and then we find its magnitude. So when lambda is minus 1, we get minus 1 minus 2, 6 minus 2, and 4 minus minus 1. That's minus 3, 4, and 5. So the shortest distance is going to be Pythagoras to that. My 3 squared, my 4 squared, and my 5 squared. 9, 16, and 25 is 50, so it's root 50, or 5 root 2. Okay. We're now going to find the shortest distance between this line and this line, which are parallel. Obviously, they're parallel because they have the same direction vector right here. Now, in my videos, you may have seen me do something where it's similar to the process we'll do for this one with skew lines in just a second, and we do a substitution where we say that t is equal to lambda minus mu, or mu minus lambda. But actually, I found a new method for this that I can teach you very quickly in this video that will make life a lot easier. So if we're trying to find the shortest distance between two parallel lines like this, well, this distance is the same as this distance, which is the same as this distance. All of the distances are the same absolutely anywhere. So if I just found a point that was on one of the lines, and I found the shortest distance between that point and the line, then I found the shortest distance between the parallel lines. So I'm going to just change this question, and instead of it being the shortest distance between a point and a line, two parallel lines, I'm going to change to shortest distance between a point and a line. It just is going to be so much easier, and then it's exactly the same sort of technique as this. So the point, I will take this one as my point. I'm going to do my 2, my minus 4, my 2. And my line that I'm going to do is the r equals 0, 2, 6 plus lambda 1, 2 minus 1. Oh, hold on a second. That is exactly the same as this question that we've got up here. So I've done this to try and save some time in this video. This is the same as the previous question. So I've done that deliberately. Obviously, you're not going to get something like this in the exam, but I just wanted to show you, if you want to go from two parallel lines, you can change it. and do the distance between a point and a line instead. Now here is one of the big ones, the shortest distance between two skew lines. It's very similar to the previous one. You find a vector between them, which was the thing that we kind of did in red. You then make it perpendicular to the direction vector of both of them, this one and this one that we've got here. You'll then get two equations. Here we only got one equation that was just to do with lambda. You're going to get two equations with lambda and mu. You solve them simultaneously for lambda and mu, you sub them back into this red vector, and you find the magnitude that goes with this. So I'm definitely going to want these written as combined vectors. My 2 plus 3 mu, my minus 1 plus 4 mu, and my 1 minus mu. This one is my 2 lambda, my 2 plus 3 lambda, and my 4 minus lambda for these two different lines here. So the vector between, I'm going to subtract them, okay? To subtract them, I'm actually just going to do, like that one, subtract that one. I'm going to see if I can sort of save a bit of time of writing these things all out. So that's my 2 plus 3 mu minus 2 lambda. I then have a minus 1 minus 2, which is minus 3. And I still have the 4 mu and a minus 3 lambda for this, okay? And then I have a 1 minus 4, which is minus 3. I have the minus mu and a minus lambda, which is a plus lambda for this one. So what I now want to make sure is that when I do that vector, my 2 plus 3 mu minus 2 lambda, blah, 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 I'm going to dot that with, this is when I try and do too much and talk at the same time. I'm going to dot that with the two vectors that I've underlined in purple, and I'm going to make them equal to 0 so that it's perpendicular to both of them, okay? So should I do that both at the same time? Yes, why not? There's so many places when you're doing this topic that you can make a mistake because there are just so many things to copy. There's so many positives and negatives, and it's just honestly one of the easiest topics to make a mistake in. So now that I've got this set up, I'm just going to find out two equations in lambda and mu, and then I'll solve them simultaneously. Let's see how quick we can go. So that's going to be timesing everything in the top by 3. 6 plus 9 mu minus 6 lambda. Everything by 4 here. So it's minus 12, 16 mu and minus 12 lambda. And everything by minus 1. 3 mu minus lambda equals to 0. Okay, I'll tidy this up a bit. So for the mu's, I have 9, 16 and 1. That's 26 mu. For the lambdas, minus 6 minus 12 minus 1. It's minus 19 lambda. Because it's going to be a simultaneous, I'll put the numbers on the other side. The minus 6, the plus 12, and the minus 3. And that is equal to 3. And then this one, doubling these, that's 4 plus 6 mu minus 4 lambda. Tripling these, minus 9 plus 12 u minus 9 lambda. And then minus 1, that's a plus 3, a plus mu, and a minus lambda being equal to 0. Further maths is no joke, right? 6 plus 12 plus 1 is the 19 mu's. For the lambdas, there is a minus 4, a minus 9, and a minus 1, which is minus 14 lambda. Did I say lambda? No, I think I've got these written the wrong way around. No, I have done that right. The lambdas. The minus 4 lambda, the minus 9 lambda, the minus lambda is minus 14 lambda. And then the constants for the other side is the minus 4, the plus 9, and the minus 3, which is equal to 2. Okay. Normally in like a maths video, I might go a little bit slower than this. I'm hoping I'm not going too fast. I'm hoping that you can pause it and look at the things that you need to. So let's just quickly recap what we've done. We have found the vector between the lines. We made the vector perpendicular to the direction vectors of each line to get two equations. We're going to solve them simultaneously for lambda and mu. We'll put them back in here, and then we find the magnitude. Okay, I was going to try and draw a diagram for it like I did for this one, but actually it's pretty complex for these ones, so we just have to kind of trust the process or try and imagine things in 3D. So the simultaneous are 26 minus 19 and 3, 19 minus 14 and 2, and I have that mu is 4/3 and lambda is 5/3. So I'm going to sub it into this one, which is just the same as this one. And I'm going to write this as 2 plus 3 lots of mu is 12/3. 2 lots of lambda is 10/3. Minus 3 plus 4 lots of mu is 16/3. 3 lots of lambda is minus 15 thirds. And then I have minus 3 minus mu plus lambda, which is 5 thirds. And we're just going to do a lot of typing in. So it's 2 plus 12 thirds minus 10 thirds. That's 8 thirds. Minus 3 plus 16 thirds minus 15 thirds. I go speedy by using the division button instead of the fraction button. Minus 3 minus 4 divided by 3 plus 5 divided by 3. And that is minus 8 thirds. On to the very last point. We now need to just find the magnitude of this. So the shortest distance is the square root of 8 thirds squared, 8 thirds squared, 8 thirds squared. Or you could just do 8 thirds squared and triple it. So 8 thirds squared times 3, square root the answer. And we have 8 root 3 over 3. Pretty mega example, this one, and they have asked this kind of question before, and it had horrible numbers with it as well. And then we get a slight break before we then do reflecting a line in a plane. This time we are looking at the shortest distance between a point and a plane, and then we'll do parallel planes afterwards. And this is the one where you just open up the formula booklet, and you're going to use this. Here is your point, alpha, beta, gamma. Your plane, where n1, n2, and n3 are the components of the normal vector. For some reason, they prefer it in this form. Normally, we have the constant on the right-hand side, but they've put it onto this side and had it as a positive. We just need to make sure it looks like this before we use the formula. The numerator are the alpha n, alpha n1, beta n2, gamma n3 plus d. Make sure you notice there's these modular signs here. And the denominator is just the magnitude of the normal vector. So in this case that we've got, I'm going to quickly rearrange this one. I know it's very obvious, but I'm going to do it as plus 5 equals 0 so that it looks exactly like the formula. Obviously, this is our alpha, beta, gamma, our n1, our n2, our n3, and d. So this means for this question that the shortest distance is going to be equal to the magnitude of the 2 and the n1 and the alpha, so that's a 2 and a 2, the n2 and the beta, the n3, which is a 1, and the gamma, which is a 2, and then plus d, which is plus 5, and that's all going to be divided by the magnitude of the 2 squared, the 3 squared, and the 1 squared. Remember, it's these parts that it comes from over here. So the numerator is 4 plus 12 plus 2 plus 5, which is 23. We don't need to even worry about the magnitude for this. And the denominator has a 2 squared, which is 4, 3 squared is 9, and 1 squared is 1. So it's 23 over root 14. And if we rationalize that, it's 23 root 14 over 14. And then we're going to have a look at an example where we're doing the shortest distance between the parallel planes that we have here. Now, they're parallel, exactly the same stuff on the left-hand side. The right-hand side has got a 4 and then a 6, so obviously they're not the same plane. They've got a different constant on the right-hand side, so they are parallel to each other. Now, this should remind us of when we did the two parallel lines. Instead of finding the shortest distance between these parallel planes, I'm just going to find a random point, any point on one of the planes, and I'm just going to find the shortest distance from that point. Whoops, didn't mean to do that. From that point to the plane. That's all I'm going to do. So I'm going to change it. Instead of it being parallel planes, I will change it to a point and a plane. All I need to do is just find any coordinate on either of them. I'll just do it on the first line. Find an x, a y, and a z that is on the plane. So if x is 0, let's keep it easy, and y is 0, then what would z be? Z would be 4. So 0, 0, 4 is on the plane. So I'm going to do 0, 0, 4 as the coordinate, and then for my plane, I'm going to do x minus 2y plus z. It would be a minus 6 equals 0. And I'm just going to do the shortest distance between these things. So when I do them, I'm going to have, for the numerator, as 1 with a 0, that multiplies to 0. A minus 2 with a 0, that multiplies to 0. A 1 with a 4, okay, good. And then the letter D is minus 6. And that's going to get divided by the magnitude of the 1 squared, the 2 squared, and the 1 squared. So 1 squared, 2 squared, and 1 squared, that is a root 6. So the numerator is 4 minus 6. That is minus 2, but there's a modulus sign. So it's 2 over root 6. And 2 divided by root 6, when we rationalise the denominator, is root 6 over 3. We are on to the last sort of skills example, which is reflecting a line in a plane, and then we will have a look at an example with some things to do with modelling. Now, the reason I've only done the reflecting a line in a plane, you also do need to know how to reflect a point in a plane, but I kind of talk about that as this middle section, which is this part here where we're finding a second point. So the aim in this question, we're going to reflect this line in this plane, is to find 2 points on the new line and then find its equation. So this plane that we've got here, I'm just going to draw it in sort of like from the side angle like this. This is the equation of the plane. And I'm going to say that this line that we've got over here, I'm going to say this is the old version of the line. Okay, I'm just going to call it the red one. When we reflect it, it is going to be something that looks a bit, if it's going to play ball, it's going to look like this. So this is the reflected line. The idea of what we're doing is we need to find 2 points on that purple line. Well, one of them is going to be where the red line crosses the plane. Okay, that's going to be one of the points. The second point we're going to find is by taking a point on the red line and reflecting it to the other side of the plane like this. Okay, the way we're going to do that is like this. I know it's not going to let me to do that, so what I'm going to do is just leave it. Let me try it one more time, and then I might put the dots on afterwards. Great, I'm going to just do this and pretend I put the dot in the perfect place. Okay, we're going to reflect that point all the way across to the other side. And then once we've got this point and this point, the green one and the black one, we can just find the equation of the line that goes through it. So this is what I'm describing here. We're going to find the first point, which is the intersection of the line and the plane. We're going to find out that black dot. We're then going to find an equation of the line through a point on the line and perpendicular to the plane. We're going to find this one so that we can reflect the point over to here. We then find where this line intersects the plane. To find this second point, we use the doubled parameter. Whatever this parameter is, we're going to go to the other side of it as well. And then once we've got this coordinate and this one, we find the equation of the line through these 2 points that we've got here. Got it? Right, let's see how this works out. So I'm going to begin by finding the black point. So I'll do the working out for this in the black point. That means I'm going to take this line and put it into the plane to find out where it intersects. The line is 0. I'm looking at this one here and I'm just going to kind of combine that as one single vector. It's just lambda, 1, and 2 plus 4 lambda. I'm going to put that into the plane. So that's with the 3, 2 minus 1 being equal to 5. So it's 3 lambda plus 2 minus 2 minus 4 lambda is equal to 5. With the lambdas, you have 3 lambda minus 4 lambda, that's minus lambda, and then 5 plus 2 minus 2 is 5, meaning lambda is equal to minus 5. When lambda is minus 5, the value of r is, using this or this, it's the same thing, is minus 5, 1, and 2 minus 20 is minus 18. Okay, 2 minus 20. I substituted it in here. So this means that this coordinate is minus 5, 1, minus 18. We have found the first point. We are now going to be trying to find this reflected point. I'm going to try and reflect this point to this one. Well, what is this point? We need a point on the red line. I think the easiest one to pick is the 0, the 1, and the 2. Okay, I think that's going to be the easiest one to reflect. So now what we're going to try and do is we are reflecting 0, 1, 2 over the plane. By the way, I use this capital pi here to show the plane. You've probably seen that before, right? Now we need to come up with the equation of this line. We're finding the equation of the line through the point on the line that is perpendicular to the plane. Well, I've got a point, I just need a direction. The direction of this is the normal to the plane. It's clearly perpendicular to the plane. 3, 2, and minus 1. So this is 3, 2, and minus 1. This means that the line is r equals 0, 1, 2. I've already used lambda, so I'm going to use mu with the 3, 2, and minus 1. If I combine this, that is 3 mu, 1 plus 2 mu, and 2 minus mu. So to reflect it, I'm going to find out where this green line intersects the plane, and then I'll be able to figure out what this one is, doing this last thing with the doubled parameter. So we're doing that same process that I just did in the black writing up there. That's my 3 mu, my 1 plus 2 mu, and my 2 minus mu, dotted with the 3, the 2, and the minus 1, and equaling 5, and coming up with some sort of equation. 9 mu plus 2 plus 4 mu minus 2 plus mu equals 5. So that's 9, 10, 11, 12, 13, 14 mu. The 2's cancel, is equal to 5. And so mu is equal to 5 over 14. Now let's just figure this out, because I don't even really need to find out what this coordinate is. I have just seen, right, that here, what colour should I do this in? I'm just going to stick with blue. At this point, mu was equal to 0. At this point, mu is equal to 5 over 14. So to go from here to here, mu has gone up by 5 over 14. So it's going to go up by 5 over 14 again. In other words, it's doubled 5 over 14. So this means that the value of mu over here is going to be 5 over 14 doubled, and 5 over 14 times 2 is just 5 over 7. So this now tells us, if I continue with this question, that the second coordinate, second point, or the reflected point, let's call it that, the reflected point is where mu is equal to 5 over 7. And I'm just going to put that into this equation that we've got. So that's 3 times 5 over 7, 1 plus 10 over 7, and 2 minus 5 over 7. So we have 15 over 7, 1 plus 10 over 7, that's going to be 17 over 7. I don't even need the calculator for that. 2 minus 5 over 7, I think that's 9 over 7. It is. Now, I can't get rid of the sevenths here because it's talking about a point, but I've now worked out that this point that is right here, which is a very important one, is 15 over 7, 17 over 7, and 9 over 7. So I'm going to highlight in yellow the ones that are the most important. I've now worked out this coordinate and this coordinate, so I can use those two things to find the equation of the purple line. So all that's left to do here, which I shall do in purple, is I'm going to find the direction of the line. So the direction, and I'm going to be using, I like to highlight things so I know which ones I'm talking about, this one and this one. The direction is going to be one of them subtract the other one. So it's going to be 15 over 7 subtract negative 5, 17 over 7 subtract 1, and 9 over 7 subtract negative 18. So 15 over 7 plus 5, that's 50 over 7. Horrible numbers. 17 over 7 minus 1, that's 10 over 7. 9 over 7 plus 18 is 135 over 7. Remember, it's a direction vector, so we can do some scaling here. So if I times everything by 7, that's 50, 10, and 135. And if I also go and divide it by 5, I've got 10, 2, and 135 divided by 5 is 27. So to go from here, I divide it by 5, and to go to here, I times by 7. So I've now finally got a direction of the purple line. I know a point that is on the purple line, so I can put the equation together, and we have that r is equal to the, what was it, minus 5, 1, and 18, and minus 18, I should say. I've already used lambda and mu, so I'm going to use t, and I'm going to use 10, 2, and 27. Hence, the reflected line is this one right there. Crazy, crazy stuff. Lots and lots of different processes. Very easy to kind of forget all of the different stages that are happening in this kind of very intense question that we have. Now, one thing I'll say is instead of this minus 5, 1, minus 18, you could have put this other yellow coordinate here. And again, instead of this direction vector, we could have used 50, 100, 135. We could have even used the one with the sevenths and stuff in it as well. So we will finish off with a modelling question. And when you do these modelling questions, all you really need to do is read through and decide which of these many skills we've been looking at the question is asking you to use, and then just go ahead and actually use those skills. It's usually intersections, angles, shortest distances. Yeah, there might be some other things, but this is generally the sorts of stuff that we will be thinking in these questions. Let's read through it and finish off this incredibly massive video. So, a scientific investigation on Mars discovers signs of alien life deep inside a mountain. Relative to a fixed origin, the face of the mountain is modelled as a plane. Okay, that seems pretty important. The face of the mountain is being modelled as a plane with this equation. And the signs of alien life are centred at this point. The units are in hundreds of metres. Calculate the shortest distance needed to drill through the face of the mountain to reach the signs of alien life. And look, we've got this idea of shortest distance. So all this question appears to be asking about is this. For A, it wants us to find the shortest distance between the mountain face, which is a plane, and a point, which is the signs of alien life, right? So the plane in this case is 2x minus 3y plus z equals minus 5. And the point is 2 minus 4 and 2. Oh, there was supposed to be a comma there. It seems to have disappeared. The shortest distance between the plane and the point. Well, we just need to find the shortest distance between this plane and this point. Oh, look, these numbers should look familiar. The shortest distance between this plane and this point. We did it earlier, and it was 23 root 14 over 14. I've tried to make this video as sort of like streamlined as possible so that we're not here for 4 hours. So I say we did it before. We did it before. The distance was equal to 23 root 14 over 14. However, this is a modelling question, so I don't want to go with exact. I'll do 23 root 14 over 14. This is 6.147. Remember, though, it is in hundreds of metres, so I shall times it by 100, and I'll give it to 3 significant figures. 615 metres to 3 significant figures. Okay, we then have some new information for the second part. A pre-existing tunnel is discovered. Maybe the aliens have already made tunnels in their mountain. It is modelled as a straight line, which doesn't seem very realistic, does it? With the equation r equals 0.26 plus lambda 1,2 minus 1. The question says, determine, or maybe I'm just going to do a quick thing here. I'm just going to highlight the fact we're talking about a line, right? So we're now talking about that the tunnel is a straight line, and this is the equation of it that we've got. Determine whether it will be shorter to drill through the face of the mountain or from a point along the pre-existing tunnel. Obviously, this is to try and reach the signs of alien life. So is the distance going to be quicker from the plane or from the line? So I think what we need to do is find out what is the distance between the point and the line. So for part B of the question, we are actually looking for the shortest distance between a line and a point. The point is the same one. It's where the aliens we think are going to be, the 2, the minus 4, and the 2. The line is the 0.26 plus lambda 1,2 minus 1. Oh, well, wouldn't you know it? We also answered this question earlier on. So we have the shortest distance between a point and a line. Here is the point, the 2, 4 minus 2. Here is the line. We did it earlier, and the distance was 5 root 2. So I'm going to save us some time. We're not going to do the same things again and again and again. We did it earlier. What did I say? We did it before. We did it before, and the distance was 5 root 2. Again, it's in the modelling context, so this is 7.071. Times it by 100 to get it in metres, and it is 707 metres to 3 significant figures. So because 615 is shorter than 707, it's going to be quicker to go from the mountain than it is to go from the tunnel. It's going to be a shorter to drill from the face through the face of the mountain. So I can say, as 615 is less than 707, it is shorter from the face of the mountain. And as always, in these kinds of questions, they like to say, let's criticize the model. Now, there's plenty to criticize in this model. We could say something like, it is unlikely that the face of the mountain is going to be a flat plane. It is unlikely that the tunnel is going to be a perfectly straight line. It is unlikely that the signs of alien life are concentrated at one single coordinate. It may be better to model it as like a larger area. If they asked us about where it would be quicker to drill through, we could also say things like the materials might be different. There might be different kinds of stone nearer to the tunnel. There might be different kinds of stone nearer to the surface of the mountain. All sorts of things to criticize like that. I'm just going to pick one of them. And the one that I'm going to pick for this is I'm just going to say that it is unlikely the tunnel is a perfectly straight line. But you could say many things that I'm sure would be accepted. It is unlikely that the tunnel is a perfectly straight line. Okay, that is the end of this absolutely mega video. I have recorded this video twice before. This is my third time of recording it, and I've had tech issues with both of them. So you may have watched a 1 hour vectors video. I have planned all of this, and then I have filmed 3 hours of vectors content. I really hope this is a good summary of a very, very challenging and huge chapter. I hope it's going to kind of bring you up to speed, but please do make sure that you're not just using this as your way of teaching, that you are using it as like a little refresher for stuff. The last thing I'm going to say is, if you are interested in applying for a scholarship where you can be awarded £150, I run something every year called the Bison Maths Award. It is currently open at the time of this video being uploaded, but if it's in the future, just search on YouTube Bison Maths Award. It may be currently open and something that you can apply for. Wishing you the absolute best of luck with your studies, and I hope to see you in another video sometime soon.